MLOps Exam Week 1-2 Introduction to MLOps can explain in own words the common issues when deploying into production if AI people do not work together with software folks without collaboration. Several critical issues arise. Usage and constraints, uncertainty about how to use the model correctly and its specific limitations. Data and problem, lack of clarity on what data is being used and which specific problem the model solves. Bias and changes, unknown functioning of the model regarding bias and what has changed in newer versions. Can explain in own words that MLOps, DevOps on their own isn't a solution. Tools and methodologies like MLOps or DevOps are not magic solutions. Communication is the fundamental layer required to make them work effectively. Without good communication, even the best ops practices will fail. Can explain the fundamental part of teamwork, communication. Good teamwork relies on communication, which involves aligning goals, regular meetings to ensure everyone is on the same page, shared tools, using common platforms for code and data to facilitate collaboration, feedback loops, quick iterations based on feedback. Trust. As per Lencioni's pyramid, trust is the foundation that enables constructive conflict, commitment, accountability, and results. Can explain the term MLOps. MLOps is the discipline of integrating machine learning models into production environments. It applies DevOps principles and practices to automate and streamline the entire M lifecycle, fostering collaboration between data scientists and developers to ensure reliable and efficient deployment. Can explain in own words the ML lifecycle, including each step: train, save, test, serve, monitor. The ML lifecycle consists of 5 key steps. 1. Train. Use data to train the model and minimize error. 2. Save, serialize, and save the trained model artifacts, weights, configurations. 3. Test. Validate performance on unseen data to check for accuracy and of a fitting. 4. Serve. Deploy the model to production, e.g., as an API for real-time predictions. 5. Monitor. Continuously track performance and detect data drift in production. Can compare the ML lifecycle with the standard software development lifecycle, including each step of these lifecycles: software lifecycle, code, build, test, deploy, monitor. ML lifecycle: train, save, test, serve, monitor. Key differences: training's coding. ML training combines code plus data, whereas DevOps starts with code. Testing. ML testing always requires data, where a software testing might not. Monitoring. ML monitoring includes checking for data drift, performance over time, not just system health, real time. 1. Can explain in own words the ops part of ML ops and DevOps. Ops stands for operations. It focuses on the processes that ensure the application or model runs smoothly in production. It emphasizes the collaboration between development data teams and IT operations to automate deployment, monitoring, and maintenance tasks for reliability and scalability. Can explain in own words the challenges in ML ops, data versioning, keeping track of changes in datasets. Experiment tracking, logging parameters and results to manage model iterations. Reproducibility, ensuring that experiments can be replicated with the same results. Scalability, handling increased loads and larger data size sufficiently. Can explain in own words how communication aligns goals and the aspects that are needed for good communication. Communication aligns goals by ensuring regular touchpoints, meetings, so team members move in the same direction. Aspects needed include shared tools, common platforms, to reduce friction and feedback loops for quick adaptation. Trust is also essential to allow for open conflict and commitment to decisions. Can explain and apply ML ops best practices. Version everything. Code, data, and models must be versioned. Automate workflows. Use CI/CD to reduce manual errors. Collaborate effectively. Implement regular stand-ups and shared documentation. Security first. Ensure secure data handling and access controls. Can draw and explain in own words ML DevOps and the double infinity schema of ML ops. The double infinity schema represents the integration of the ML cycle, data model code, and the DevOps cycle, plan, release, configure. One loop focuses on the experimental nature of ML, curate, train, validate. The other loop focuses on the operational stability, package, release, monitor. They intersect, showing that MLOps is the continuous flow between developing models and operating them in software systems. Can explain in own words how to completely incorporate MLOps and DevOps. MLOps and DevOps can be incorporated by synchronizing their stages. Planning. Devs and data scientists define requirements together. Development. Application code and ML pipelines are developed in tandem. CI/CD. Testing, packaging, and deploying are applied to both the software app and the ML model simultaneously, treating the model as a software component within the larger system. Can explain DTAP in context of MLOps, including the types of data used. DTAP stands for development, testing, acceptance, and production. In MLOps, the data types change across stages. Development D uses test data for initial experiments. Testing T uses test data or AI-generated synthetic data twins to validate functionality. Acceptance A uses test data or synthetic data for user acceptance. Production P uses real data live traffic. 2. Can create an own CI/CD pipeline for AI projects to create a CI/CD pipeline for AI. 1. Search for tools. Identify local cloud tools, e.g. Docker. 2. Create app plus model. Develop the model in the wrapping application. 3. Production code. Convert notebooks into production-ready scripts. 4. Pipeline setup. Configure a pipeline to automate steps, train, test, deploy in a DTAP environment. 5. Trigger. Configure the pipeline so that new data triggers automatic retraining and rollout. Week 2. 1. Data management and versioning can describe in own words the role of data in MLOps. Data is a key component in MLOps, as models rely on it for training, evaluation, and inference. Challenges: data consistency, availability, scalability, and quality. Importance: proper data management ensures reproducibility, traceability, and collaboration. Can describe in own words the term data management. Data management is the process of collecting, organizing, storing, and maintaining data to ensure its quality, consistency, and accessibility throughout the M lifecycle. It enables reproducibility and efficient collaboration. Can describe in own words the term well-governed data management process. A well-governed process ensures data is handled in compliance with policies and regulations, e.g., GDPR, HIPAA. It involves strict access controls, auditing usage, and maintaining security through encryption to prevent unauthorized access and ensure integrity. Can list 4 key data management tasks. 1. Data ingestion, collecting raw data from sources. 2. Data cleaning, handling missing data/anomalies. 3. Data transformation, pre-processing data in taussable formats. 4. Data governance, policies for security and compliance. Can list 4 challenges in data management for MLOps. 1. Handling large volumes, structured, unstructured, real-time batch scaling. 2. Data silos, disconnected systems preventing integration. 3. Data quality and consistency, incomplete or noisy data. 4. Compliance, adhering to regulations like GDPR. Can describe in own words the term data silos. A data silo is an isolate repository of data within a specific system department that cannot be easily accessed or integrated with other sources. This limits collaboration, creates inefficiencies, and complicates governance. Can describe in own words the term data versioning. Data versioning is the practice of tracking and managing multiple versions of a dataset to ensure consistency and reproducibility. It allows teams to revert to previous versions, rollback, and ensure models are trained evaluated on specific, known data states. Can list and explain the 5 importances of data versioning. 1. Reproducibility. Ensures experiments can be reliably reproduced with the X3. Act dataset used. 2. Traceability. Provides a lineage of changes to trace errors or performance issues. 3. Collaboration. Enables teams to work on different versions without conflicts. 4. Rollback capability allows reverting to previous versions if new data introduces bugs bias. 5. Compliance and governance maintains a record of changes for audits and regulations. Can list and explain in own words the 4 levels of data versioning one dataset, tracking versions of raw processed data files. 2. Metadata, tracking schema, timestamps, lineage, and transformations. 3. Feature, versioning engineered features, e.g., specific columns calculations. 4. Model data mapping, mapping specific model versions to the exact data versions they were trained on. Can describe in own words the term data lineage. Data lineage is the process of tracking the origin, movement, and transformations of data as it flows through a system. It provides a traceable path for transparency, accountability, and auditing. Can list and explain 4 best practices of data versioning in MLOps 1. Identify critical data. Version only data impacting model output, training/testing sets. 2. Version metadata. Track schema and pipelines along with data. 3. Use storage with versioning. Use a tool's DVC, Delta Lake, or cloud buckets with versioning. 4. Automate in pipelines. Integrate versioning steps into CI/CD. Can explain how to integrate data versioning in an MLOps pipeline, CI/CD integration. Automate dataset versioning during ingestion/deployment. Reproducibility. Configure pipelines to retrain models using exact version data. Lifecycle tracking. Monitor data from pre-processing to production. Drift handling. Use a versioning to detect drift and trigger retraining. Can describe in own words the term data drift. Data drift is the change in the statistical properties of data over time, e.g., input distribution changes. It causes models to perform poorly because they are trained on outdated data patterns. Can describe in own words 3 types of data drift, including impact and mitigations. 1. Covariate drift, feature drift. Input feature redistribution changes, but relation to target stays same. Impact, accuracy drop on new data ranges. Mitigation, monitor distributions retrain with recent data. 2. Prior probability shift, label drift, target variable distribution changes. Impact, bias towards majoriticless. Mitigation, adjust thresholds, retrain with balanced data. 3. Concept drift, relationship between input features and target variable changes. Impact, model becomes outdated, fails. Mitigation, online learning, drift detection triggers retraining. Can explain how to ensure data security and compliance in MLOps governance policies, enforce privacy, GDPR, and ethical standards. Access control, implement strict access and encryption for storage. Monitoring auditing, track all data changes and access logs for 4. Accountability, can set up data management and versioning for an MLOps pipeline toast-up. 1. Research select tools, e.g. DVC, Pachyderm, or local GitLFS. 2. Automate ingestion, create pipelines that version new data upon arrival. 3. Production code, refactor notebook code into reusable scripts. 4. Quality control, implement monitoring, e.g. Great Expectations to flag bad data. 5. Lineage, ensure full tracking from ingestion to model training. Week 3, 1. Model training and experiment tracking, can describe in own words the terms model and model training. Model, a trained machine learning artifact that encapsulates learned parameters, algorithms, and structural design, e.g., layers, trees, to make predictions in new data. Model training, the process of teaching a model to perform a specific task by adjusting its internal parameters based on input data to optimize performance, minimize error/loss. Can describe in own words the terms experiment and experiment tracking. Experiment, the process of training and evaluating a model using a specific set of data, algorithms, and hyperparameters to assess performance. Experiment tracking, systematically recording and managing all details of an experiment, data, params, metrics, to ensure reproducibility and comparison. Can list 4 reasons why model training and experiment tracking are useful in MLOps. 1. Efficiency and scalability, automating training/logging accelerates cycles. 2. Collaboration and transparency, centralized records allow teams to share progress. 3. Reproducibility, ensuring models can be recreated for validation debugging. 4. Performance optimization, comparing versions to find the best configuration. can list 3 key aspects to integrate model training and experiment tracking in MLOps 1, automated pipelines, handling end-to-end lifecycle, processing to deployment. 2. Experiment logging, tracking details for comparison. 3. Continuous monitoring and optimization, ensuring ongoing performance. Can list 4 challenges that can occur while iterating model training and experiment tracking in MLOps 1. Reproducibility issues, inconsistencies in environments data. 2. Resource constraints, bottlenecks with large models datasets. 3. Complex experiment tracking, managing numerous variables becomes overwhelming. 4. Scalability maintenance, handling concurrent jobs and pipeline complexity. Can describe in own words the term machine learning model management. Model management is the process of overseeing the entire life cycle of ML models. It includes packaging, lineage, monitoring, retraining, log-geeing, and versioning to ensure models are reproducible, maintainable, and scalable from development to deployment. Can list and describe in own words model packing, model lineage, model 5. Development and deployment, monitoring and model retraining, logging, code data and pipeline versioning in context of MLOps, model packaging, bundling the model with dependencies, code, libs into a deployable format, e.g. Docker container. Model lineage, tracking the complete history, data sources, code, params of a model version. Development and deployment, automating the path from creation to production, CI/CD. Monitoring and retraining, detecting degradation/drift and triggering updates. Logging, capturing detailed records of runs, metrics, params for analysis. Versioning, tracking all components, code, data, pipeline to ensure reproducibility. Can list 4 best practices for model versioning in MLOps 1. Track models alongside code and data. Version everything together. 2. Assign unique identifiers. Use hashes version numbers for every model. 3. Log model metadata. Store params and metrics for comparison. 4. Automate versioning and pipelines. Integrate into CI/CD to avoid manual errors. Can set up model management in a MLOps pipeline to set it up. A model registry, e.g. MLflow, to manage versions. Integrate with CI/CD, e.g. Jenkins, to trigger training and autolog results. Ensure every training run is logged as an experiment. Commit. Automate the promotion of models from registry to deployment. Week 4. 1. Deploy. Monitor and manage models in production. Can describe in own words the term deployment in context of a machine learning model. Deployment is the process of taking a trained machine learning model from the development environment and integrating it into a production system where it can be used to make predictions on new, real-world data. Can list and explain 3 ways how to embedded ML models with production systems. 1. Applications. Directly embedding the model code or artifact into an end-user application, e.g. mobile app, desktop software. 2. Services. Exposing the model as a service, e.g. REST API, microservice that other systems can call to get predictions. 3. Workflows. Integrating the model as a step in a larger data processing pipeline or workflow, e.g. batch processing jobs. Can list and explain 2 aspects where compatibility must be ensured while deploying a ML model. 1. Software environment. Ensuring libraries, dependencies, and language versions match between dev and prod, e.g. Python version, TensorFlow version. 2. Hardware environment. Ensuring the model runs efficiently on the target hardware, e.g. CPU vs GPU availability, memory constraints. Can list and explain 3 aspects to watch for during the integration with a production system. 1. Inference mechanisms. Setting up the serving infrastructure, on-prem versus cloud, containers to handle requests. 2.6. Performance and reliability monitoring. Ensuring latency is low, uptime is high, and the system can handle the load. 3. Security and compliance. Protecting sensitive data, encryption, and adhering to regulations, GDPR. Can explain in own words why the different environments must be as identical as possible. Environments, DTAP, should be identical to ensure a consistency. If environments differ, a model might work in development but fail in production due to missing dependencies or configuration mismatches. It works on my machine syndrome. Identical environments prevent these surprises. Can describe in own words the term model registry. A model registry is a centralized repository system that stores trained ML model artifacts along with their associated metadata, versions, metrics, dependencies. It enables efficient management, tracking, and retrieval of models for deployment. Can describe in own words the term ML metadata store. An ML metadata store is a centralized repository that collects all metadata generate throughout the ML lifecycle datasets used, experiment configs, model params. It facilitates reproducibility and traceability by linking artifacts to their creation context. Can describe in own words the term model monitoring. Model monitoring is the continuous process of tracking the performance and behavior of models in production. It involves detecting issues like data drift, concept drift, or performance degradation to ensure the model functions as intended. Can list and explain 4 aspects to monitor in a MLOps system. 1. Service health, uptime, latency, and resource usage, CPU memory. 2. Model accuracy performance, real-time metrics like precision, recall, or error rates, if ground truth is available. 3. Data drift, changes in the distribution of input data compared to training data. 4. Bias fairness, ensuring the model doesn't develop biases against specific groups over time. Can explain where it's advised to monitor in the MLOps flow. Monitoring should happen everywhere. Data ingestion, check for data quality/schema changes. Training, monitor metrics and resource usage. Deployment, check for successful rollouts. Inference, monitor predictions, latency, and drift on live data. Can explain the usefulness of model updates, rollbacks, and notifications. Updates, allow improving the model with new data or algorithms to maintain accuracy. Rollbacks, crucial for quickly reverting to a previous stable version if a new update fails or underperforms, minimizing downtime. Notifications, alerting, essential for proactive maintenance, informing the team immediately when metrics cross thresholds, e.g. error rate 5%. Can set up deployment and monitoring of ML models in an MLOps system. To set this up. 1. Deploy, package the model, e.g. Docker, set 7. Up a CI/CD pipeline, Jenkins/GitLab, to automate deployment to an API, Flask Fast API. 2. Monitor, integrate tools like Prometheus to scrape metrics and Grafana to visualize them. 3. Configure define metrics, latency, drift, and set up alerts to notify engineers of issues. 8.